Okay, in this lecture we're going to continue through our section 3.4 material on partial fractions. And we mentioned in the first part of this section that we would use the method of partial fractions to integrate a rational function, so that is a quotient of two polynomials, where the degree of the numerator is less than that of the denominator. And in our first lecture, we had seen how to handle the case that our denominator involves either distinct linear factors or some repeated linear factors. So the next cases that we'll consider involve what are called irreducible quadratic factors. So to illustrate this case, let us consider the following. So this is known as case 3, or the case of distinct irreducible quadratic factors, which says if our denominator of the rational function q of x contains distinct irreducible quadratic factors, then the decomposition would look slightly different. So first, let us talk about an irreducible quadratic. What do we mean by that? So to illustrate this, let's say that we have something of the following form, where our denominator can be factored as x squared plus 1 times x plus 2 times x plus 3. Now, this first factor that appears in our denominator, x squared plus 1, is a quadratic, and it cannot be factored any further. That is, it cannot be factored down to linear terms unless we were to introduce complex numbers here, and we don't want to do that for our calculus sequence. So if we have some quadratic which cannot be factored any further, we call that an irreducible quadratic. Now, suppose that we have some denominator that can be factored in this way, and that irreducible quadratic term only appears once. So that is, it's not repeated. There are no quadratic factors being squared or cubed. So we would say that that irreducible quadratic would be distinct in that case. It only appears once. So here we could rewrite this function as the following decomposition. Let's say something of the form ax plus b over our irreducible quadratic, x squared plus 1. So notice already this first term looks a little different from what we worked with in the case of linear factors. Since our denominator is a quadratic here, our linear, or our numerator will no longer be just a constant, but instead a polynomial of degree 1 less than a quadratic. That would be a first degree polynomial, or something of the form ax plus b. Then we have, following that quadratic factor, two linear factors, x plus 2 and x plus 3, which are not repeated. They only appear once. So as we saw in the first part of this section, for those linear factors, or for each of our linear factors, we would have some other term in our decomposition, which would involve a constant, say c over x plus 2, or d over x plus 3. Now I could modify this a little bit to illustrate a few other cases that we might consider. So let's say that we had something of the following form. Let's say x over, let's say we have x squared plus 2 and x squared plus 3. So here my denominator involves an x squared plus 2 and an x squared plus 3, which are both irreducible quadratics, but they're distinct from one another. That is, they're not the same expression. It's not repeated. So in this case, our decomposition would have a similar form. For the quadratic x squared plus 2, I would have a term of the form ax plus b over that x squared plus 2. And then I would have another term for my irreducible quadratic x squared plus 3, where my numerator would be some different linear function, something of the form cx plus d. Or if I modify the example in the notes slightly, let's say that I changed the x plus 3 factor on the end to be an x plus 3 squared. Well, I would have my irreducible quadratic factor, my distinct linear factor, and now this last term would involve a repeated linear factor. So when I have this d over x plus 3 term, I would also need to include another factor of the form e over x plus 3 squared, since that linear term had two factors appearing. So we can see, of course, the more terms that we would have for our denominator, or if some of them are repeated, then our partial fraction decomposition gets more complicated. But nonetheless, the approach is the same as what we saw in the first part of this lecture. So let's look at an example to illustrate this case of an irreducible quadratic. So here we're asked to evaluate the antiderivative shown here, and we see that it is, our integrand is a rational function where the degree of the numerator is less than that of the denominator. Second degree numerator, but a fourth degree denominator. So that suggests that we should try this method of partial fractions. And our first step in this method is to factor the denominator as far as possible, because we need to know which of the cases we're working with. So we need to know how our denominator can be factored. Now, in this example, we see that we could factor out an x squared from the denominator, and I would be left with an x squared plus 9 dx. And this x squared plus 9 term cannot be factored any further. It is an irreducible quadratic, and we see that it only appears once. That is, there's only one factor of x squared plus 9 in the denominator. However, there are two factors of x. There's a repeated linear factor here, and my one irreducible quadratic. So, for a function that would have this form of a denominator, our partial fraction decomposition of this function would have the general form a over x plus b over x squared. Since we had an x squared term in our denominator, it's a repeated linear case. We have to have one term for each power that appeared. And then plus, well, my last term was an irreducible quadratic, x squared plus 9, which means that my numerator must be a linear function, something of the form cx plus d. So as with our earlier examples, to solve for these constants, a, b, c, and d, we can multiply both sides of this equation by the common denominator, x squared times x squared plus 9. And we would be left with 4x squared plus 18x plus 27 is equal to a times x squared plus 9 plus b times x squared plus 9 plus the cx plus d term times x squared. And here I'll illustrate first that our method we had used in the first part of this lecture, where we were trying to kill off certain coefficients, say a, b, c, or d, by plugging in values of x does not work very well when we run into these irreducible quadratics. To illustrate why, well, let's say that we're trying to get rid of this b term. So I would need to find a value of x such that x squared plus 9 is 0, but that would mean introducing complex numbers. So there's no easy value of x in some of these problems. In order to kill off those terms as we had illustrated in the case of linear factors. So if we can't get away with that, let's instead expand on the right-hand side, and we would have ax cubed plus 9ax plus bx squared plus 9b plus cx cubed plus dx squared. Or combining like terms, I would have an a plus c x cubed, then a b plus d x squared, then a 9ax, and a constant of 9b. And that has to equal 4x squared plus 18x plus 27. So equating my coefficients, starting with the highest degree term, well, I had an a plus c x cubed, and notice that on the left-hand side, well, it's only up through a second degree polynomial, there is no x cubed term. So that means that the coefficient a plus c of x cubed, well, it must be 0 in order for the left and right-hand side to agree. Now the x squared coefficient was b plus d, which must equal to the x squared coefficient 4. So we can say b plus d is 4. Our coefficient for x, which was 9a on the right-hand side, must be equal to the coefficient of x, which was 18 on the left-hand side. And our constant coefficients, 9b and 27, must be equal. So from our last two equations, we can immediately see that a would be 2 and b would be 3. Now looking at our first equation, since a plus c is 0, well, if a is 2, c is the negative of a, so negative 2. And for our second equation, if b plus d is equal to 4, and b is known to be 3, then d must be 1. So here, to illustrate that for your notes, you might say, well, we were taking the value of a and substituting into the first equation, and we were taking the known value for b and substituting into the second equation to get our c and d values. Now, once we have these values, let's look at our integral in its decomposed form. So our decomposition was of the form a over x, where a was 2, plus b over x squared, where b was 3, then plus cx plus d, where c was negative 2, so I would have a negative 2x, plus d, which was 1 over x squared plus 9, and I can split up that cx plus d over x squared plus 9 into the cx and then plus d term individually over x squared plus 9. And now each of these terms we can integrate directly. So let's see what we have here. For this first term, we would have an antiderivative of twice the natural log of absolute value x. then plus 3 times the antiderivative of 1 over x squared is negative 1 over x, so we get negative 3 over x, minus, let's think about this third term. To integrate this third term, I could make a u substitution, where u would be my denominator, in which case du is 2x dx. That's exactly what I'm going to have for my numerator. So by making a substitution, this third term reduces to the integral of du over u, and then plus the antiderivative of this last term, 1 over x squared plus 9, or x squared plus 3 squared. If you think back to the section 1.5 lecture, we derived a formula for antiderivatives of this form, and this would be given by 1/3 arctangent of x over 3. And so when I evaluate my third term, the integral involving u, I would have the following. So that would have an antiderivative of negative natural log of absolute value u, which we had as x squared plus 9, then plus my 1/3 arctangent of x over 3. And since this was an indefinite integral, we can't forget the plus c term on the end. So here we see an example where after our initial partial fraction decomposition, we might still have a couple of terms which are a little bit tricky to integrate. Say, by making use of a substitution, we could integrate that third expression, or by using, technically we used a substitution when we derived our formula for this arctangent integral. But if you have that formula memorized, as I had suggested from section 1.5, you can evaluate that last antiderivative immediately. So here we're left with the following as our final answer. Now the last case that we'll discuss, case 4, is the case that we have a repeated irreducible quadratic factor. So let's suppose that the denominator of our rational function, q of x, contains some repeated irreducible quadratic factors. So to illustrate this, maybe something of the following form, where in our denominator, we have this x squared plus 1 expression, which is an irreducible quadratic, and that expression is then being squared. So in other words, we have two factors of that irreducible quadratic. And then following that, we have a product of two distinct linear factors, say x plus 2 and x plus 3. So this case of a repeated irreducible quadratic works somewhat similar to the case of a repeated linear factor. So for the irreducible quadratic terms, x squared plus 1, well, we would have something of the form ax plus b over x squared plus 1 to the first. And since this factor was repeated, we would have to have something then of the form cx plus d over x squared plus 1 quantity squared. Now, if that term were cubed, say x squared plus 1 cubed in the denominator, we would have a third term, something of the form ex plus f over x squared plus 1 quantity cubed, and so on. So just as we saw for the case of repeated linear factors, for every power of an irreducible quadratic, we're going to have one term in our partial fraction decomposition. And for these last terms, where we had distinct linear factors, we have some constant divided by that linear factor, the same as what we had considered before. Or again, if we modified this slightly, let's say we made the x plus 3 power cubed, well, we would have two more terms, say something of the form g over x plus 3 squared and h over x plus 3 cubed, and so on. So again, the more complicated our denominator is, the more complicated the partial fraction decomposition becomes. So to illustrate this case of a repeated irreducible quadratic, let's look at the following example. And here we're asked to evaluate the antiderivative of the following rational function, where the degree of the numerator is less than that of the denominator. So when we see that, that should automatically make us think of this method of partial fractions. So the method of partial fractions requires us to first factor our denominator as far as possible. And here, the denominator, x to the fourth plus 2x squared plus 1, can be factored as x squared plus 1 quantity squared. And that x squared plus 1 expression is then an irreducible quadratic. This cannot be factored any further. So we see that our denominator involves this repeated irreducible quadratic factor. So in this case, our function would have a decomposition of the form ax plus b over x squared plus 1 to the first power plus another linear polynomial cx plus d over x squared plus 1 squared. So, multiplying through by the common denominator, x squared plus 1 squared, we have the right-hand side as given by ax plus b times x squared plus 1 to the first plus cx plus d. And expanding this right-hand side, we would have ax cubed plus bx squared plus ax plus b plus cx plus d, or collecting like terms, ax cubed plus bx squared plus a plus c times x plus b plus d. And this had to equal this x squared plus x plus 1. So equating the coefficients, well, the coefficient for x cubed, which was a, must be equal to 0, since there was no x cubed on the left-hand side. Equating the x squared coefficients, we have b would have to equal 1. So a and b we have right away. Then looking at the coefficient of x, we would have a plus c has to equal 1. And since we already knew that a was 0, that means right away that c has to be 1. And equating the constant coefficients, b plus d has to equal 1. And since b was already known to be 1, it follows that d must be 0. So we've got our values right away. So looking at our integral in its decomposed form, we had something of the form ax plus b. Now a was 0, so we just have b, which was 1, over x squared plus 1. Then plus cx plus d, where c was 1 and d was 0, so we just have 1x over x squared plus 1 quantity squared dx. Now, the first part of this integral I can evaluate directly. The antiderivative of 1 over x squared plus 1 is arctangent of x. Then we're adding the antiderivative of x over x squared plus 1 quantity squared. And to handle this integral, well, we see our denominator involves a composite function. So let's try a substitution. If u is equal to x squared plus 1, then du would be 2x dx. And rewriting this second term, in terms of u, we would have half of du over u squared. So the antiderivative would be negative 1 over u times our 1/2 gives us negative 1 over 2u plus c. But u was known, so substituting back in, we have arctangent of x minus 1 over twice u, which was x squared plus 1 plus c. All right.